Perfect. Well, good afternoon, everybody. Bonjour à tous. It's a great pleasure to be with you today. And first, I want to thank Ivado and Alexandre for organizing this great event. And today I'll talk about solving optimization problems with partial differential equations, PDEs for short. So do you know the common ground between weather prediction, spacecraft trajectories, and the heat diffusion in your room? Well, all these phenomena are modeled with differential equations. So the solution of these equations is a function that is described by its partial derivatives. So for instance, you can see here on the right, the heat map function in a square room in 2 dimensions. And this function is actually the solution of a specific PDE called the Poisson equation. The PDEs are fascinating objects present everywhere in our world, but as for every model, they contain uncertainties. For instance, they can involve hyperparameters that are usually approximated. Fortunately, nowadays, high-resolution data describing the evolution of these complex systems are becoming available, and they can be used to refine the models. So this leads to a coupling between the differential equations and a cost function to be optimized, ensuring that uncertain parameters are matching the data. So this leads to the PDE-constrained optimization problem. And we tackle here the challenge of building a code for these problems. Building a practical code requires cutting-edge technology, and we chose Julia, an open-source programming language designed for high performance. And I'm contributing here to the JuliaSmoothOptimizers, a GitHub organization of Julia packages for linear algebra and continuous optimization solvers, initiated by Dominique Orban and Abel Sicara here at Montréal in Polytechnique. And in this framework, I developed a toolbox of packages for our problem. The core package, PDE-NLP-model.jl, offers tools to model the PDE and the cost function and preprocesses the problem. Then we provide several solutions for the resulting model, interfaces to well-established solver, but also homemade solvers in pure Julia, such as DCI solvers and FPS.gl. In particular, the latter implements a factorization-free Fletcher's penalty method, specifically designed for problems of such huge scale. And finally, we also maintain the package PDE-optimization-problems.jl with test problems and applications used to compare and calibrate the solvers. To sum up in a few words, we built here a complete ecosystem for PDE-constrained optimization in Julia. So given a real-world application modeled with differential equations, one can implement the model with PDE-NLP-models.jl and then compute the solution with any of our solvers. And the resulting solution can then be printed and analyzed to learn more on the applications. So to say a few words about perspectives, more can always be done in maintaining and improving this new ecosystem, but we are also working on more complex models and bringing more concrete applications from data science. So that's it for me. Thank you all for listening, and I'm looking forward to any question you might have.